Hi, today we're going to be solving a geometry problem, and this is the 11th problem on the 2015 Aime number 2, or the American Invitational Mathematics exam. It's a pretty tricky problem, but the reason why I like this problem is because it doesn't really involve the solution I'm going to be showing you doesn't really involve any of the complicated geometry theorems that you might see on a hard Aime problem or a Olympiad style problem. So it really can only be solved using techniques that you learn in a regular geometry class in high school. So without further ado, let's get started. So as with any geometry problem, you want to have a good, big, clear figure to work with. So I'm going to start by drawing triangle ABC that the problem talks about, and label its 3 vertices. And then it tells us that we have a circumcenter, which is going to be denoted by point O. And we have a segment BO. And it tells us there's a segment that's perpendicular to BO. And it intersects AB at point P and line BC at point Q. And then it gives us a couple of lengths. It tells us that AB is equal to 5. It tells us that BC is equal to 4. And it tells us that QB is equal to 4.5, which means that QC is equal to 1/2. So now we know that these two lines are perpendicular, so I'll draw that in. So now this diagram, we have everything from all the information from the problem on it. But one thing we haven't really used yet is the fact that O is a circumcenter. So that means it's a special point in the triangle. And what that means is O is the center of a circle that is circumscribed about the triangle. And it is actually formed by the intersection of the perpendicular bisectors of the 3 sides. So that means the intersections of the perpendicular bisectors, they will be concurrent at point O. And so I'm going to draw in one of those perpendicular bisectors, and we'll work from there. So let's call this point D. And if it's a bisector, that means that these two lengths, BD and DC, are equal. So that means it's 2 and 2, because 2 is half of 4. And from here, we start doing the interesting stuff. So we see we have 2 right angles here, one right here and one right here. And this looks like a pretty familiar configuration. We have 2 pairs of similar triangles here. So I'm going to be working with triangle BDO. And we know that because this angle right here, angle BDO, is a right angle, as well as BOQ is a right angle, that the two, and then we share this common angle right here, this is common to the 2 triangles, we have similar triangles. So we'll set up a ratio, and we're going to try to solve for side BO right now. And the reason we want BO is because it is actually the radius of the circumcircle, because O is the center and B is a point on the circle. So that means this is a radius. So let's set up that ratio. So we know that 2 to, we're going to call the segment OB, is equal to OB to 9/2. So looking at our triangles, we see 2 to OB is equal to OB to 9/2. So that can be easily seen using similar triangles. And then we have OB squared is equal to 9, so OB equals 3. So now we have a new side length. We have OB is equal to 3. And we also know that OA is congruent to OB because they're both radii of the circle. So that means we know OA is also equal to 3, which is pretty useful. So now we have an isosceles triangle AOB right here. And we also have another perpendicular bisector because, as I said, the circumcenter is the intersection of the 3 perpendicular bisectors. And we're going to call this point, let's say, E. And so we know that EB, we know the length of that, because remember, it's a bisector of side AB. So that means its length is 5/2. So now right here we have another interesting relationship. We know that POB is a right angle, right? Because remember, the problem statement itself tells us that PQ is perpendicular to BO. So we know this is the right angle right here. And again, this is another familiar configuration. In fact, it's pretty much the same one that we saw before with the other pair of similar triangles. We have another pair of similar triangles right here. We know that triangle BEO is similar to triangle BOP. And remember, we're trying to find the length of BP in our problem statement. So let's go about setting up another ratio. So we know that, 5/2, which is the length of BE, over 3, which is BO, is equal to 3, which is the length of BO again, over X, which we're going to say is BP. So we're just going to call BPX. So that's what BP is. So the reason why we can set up this ratio is because of the similar triangles. Again, we have 5/2 to 3 is equal to 3 to X, because BEO is similar to BOP, because they both have right angles and they share this common angle right here. And so solving this ratio, we see that 5/2 times X is equal to 9. So X is equal to 18 over 5. And so this is our final answer. 18 over 5 is the length of BP. So I'm going to write that in. And so since this is an Aime problem, remember, they want to know the fraction of BP, which is equal to m over n, and they want to know what m plus n is. And we can quickly check 18 and 5 are relatively prime. They share no common factors. And so 18 plus 5, which is m plus n, is equal to 23. So if you were actually doing the Aime test, you'd put in 23. All right, well, that ends the problem. Just a couple things to keep in mind on the approach I took. First, we drew a big diagram just to get everything clear in our head and see the picture. And then we took advantage of the fact that point O was the intersection of the perpendicular bisectors, because that's the definition of the circumcenter. And we found a lot of right angles. And once you see a lot of right angles in triangles, what do you think? Similar triangles. And that's what we really use. We use similar triangles twice to solve the problem. All right, thank you.